Hello, good morning, good evening, good afternoon, everybody, wherever it might be. It is my great pleasure to welcome Fabio Gavarini, my old friend. We were together like 2 decades ago, doing things, swimming in Adriatico and so on.
Even more, I think.
Yeah. And so, buongiorno tutti. Today we will have multi-parameter quantum groups, deformations, and specializations. It's all yours, Fabio. Take it away.
Thank you very much. Can you hear me correctly? All of you?
I can hear you perfectly.
Perfect. So thank you, Piotr, for the introduction. And let me also thank the organizers in general for inviting me to give a talk in this seminar. I will mostly report on a joint paper with Gaston Andres Garcia, with whom we worked for quite a while, let's say the last 12 years on these topics. But most of what I'm talking about is concentrated in just one huge paper who appeared online on last February, but it's not yet appeared in press. Anyway, it will be published on Annales de l'Institut Fourier. And in the last part of the talk, I will also mention some more recent works, some more recent results joined with Margherita Paolini as well. Now, multiparameter quantum groups. That's a topic who was already studied at the beginning of the story of quantum groups. But the key point is that there were mainly two different points of views, which seem to be entirely independent of each other. So we were looking with Gaston for a joint point of view, for a uniform approach, and eventually we succeeded. So let me start the talk with recalling what was known before we entered the game. In particular, I will start with uniparameter quantum groups. By the way, in this talk, almost till the end, I will mean by quantum group quantized universal enveloping superalgebras. In particular, the underlying semi-classical objects are Lie algebras, which will inherit from the quantization automatically an additional structure of being Lie bi-algebras. And in particular, for the multiparameter quantum groups that we are dealing with in a moment, these Lie algebras will be, first of all, the usual semi-simple Lie algebras, and more in general, the whole family of Kac-Moody algebras, contragradient Kac-Moody algebras, but of symmetrizable type. So let's say that we start and we fix once and for all some Cartan data. This is the combinatorial ingredients we start with. These data are given by, first of all, a generalized Cartan matrix, which has to be symmetrizable. The size is n. Symmetrizable means that we have some diagonal matrix, this D, which such that my dA is symmetric. I will call dA the symmetrized Cartan matrix. And you fix some normalization so that this D is, in a sense, minimal. Also, you need to fix a Cartan subalgebra, this German H, whose dimension will be denoted by T. Now, with this Cartan subalgebra, you also fix a choice of so-called simple roots, which are elements in the dual, simple co-roots, which are these elements H sub I inside the Cartan subalgebra. These simple roots and simple co-roots have to match nicely with each other in a way prescribed by the Cartan matrix. But anyway, out of this data, you introduce what is known as the Kac-Moody algebra, following the recipe by Victor Katz, which is given in terms of this Cartan matrix, the Cartan subalgebra, and the choice of simple roots and simple co-roots. Let me stress that now, since the Cartan matrix is symmetrizable, for this Kac-Moody algebra, we have a complete presentation by generators and relations. In general, you cannot achieve such a result. The construction is slightly more complex, but when the Cartan matrix is symmetrizable, you really have a complete description by generators and relations. By the way, with the same data, instead of presenting the Kac-Moody algebra, you can also present its universal associative algebra, universal enveloping algebra. which is an associative algebra. The presentation, for instance, in the case of semi-simple Lie algebras, is the presentation by Serre. Again, in the same spirit, you can introduce the quantum counterpart of this universal enveloping algebra, which is our quantized universal enveloping algebra. Now we have two possible formulations for it, the formal one and the polynomial one. Everything should be more or less familiar with most of you, so I'll be a bit sketchy. So let's say Drinfield's algebra. What is that? We fix as a ground ring this ring of formal series. And this will be a unital associative algebra, which will be complete in the h-adic topology, given by a presentation by generators and relations. Generators are essentially like in the case of the Kac-Moody algebra. I will call these ones coming from the Cartan subalgebra Cartan generators, whereas the EIs and the FIs will be mentioned as being the Chevalier generators. The relations are sort of a quantum variation on the model of the relations for the presentation of the universal enveloping algebra. So for instance, we have these relations and these ones in the second line, which are exactly as in the classical case of the universal enveloping algebra of my Kac-Moody algebra. Instead here, in the classical case, you have just the simple coroot hi. Here we have a more complicated function of it. In particular, you see here you need an h-adic completion. The last line is where we have the so-called quantum Serre relations, which look almost like classical Serre relations. The difference lies here, because instead of a usual binomial coefficient, which is an integral number, you have a quantum binomial coefficient. Let me also notice that here I have, of course, two sets of quantum Serre relations, because these X might be either Chevalier generators of type E or Chevalier generators of type F.
Sorry, could you explain
so we have
this square bracket with this subscript?
Yeah, the subscript depends on the I. You have here relations depending on I. So if you, it also takes into account, if you want, the length of the simple root associated with I. Is this what?
But how it is defined?
Yeah.
It's a Q binomial that Gauss defined.
It's a ratio of quantum factorials. So instead of having the factorial of 1 minus aij divided by factorials of s and factorial of 1 minus aij s minus s, you have to replace the factorials, being integral numbers, with quantum factorials. Is that enough?
Okay, thank you.
And
no, let me Fabio, explain, because there is a very easy way to memorize it. Imagine that you have x plus y to the power n, and then you would write out the formula using the usual binomial coefficients, okay?
Yes.
And now imagine that xy is not equal yx. So imagine that xy is equal qyx. And then because you can always commute things, right, with just the price of having the power of q, you can obtain uniquely, remembering that powers of x and y are linearly independent, so you can gather coefficients uniquely. You can find and compute what are exactly these q binomials. But indeed, as Fabio, it can be written as quantum factorials, the usual formula, but instead of usual factorials, you use quantum factorials. But somehow
the subscript plays the role of this q, yes?
And the subscript is just an element of a ground, commutative ground ring.
Yeah, you might call it q, and that's so. In general, the quantum binomial coefficient is a function of q, an invertible element q. Your element q now is this subscript.
Okay, thank you. Now it is clear.
Yeah, it will be probably even more clear in a moment. Anyway, this is just part of the story, because here you are defining some associative algebra by generators and relations. Okay, no obstruction to that. The additional point is that you have something more, namely this associative algebra admits an extra structure, that of a topological Hopf algebra, where the coproduct is given on generators by these formulas. Here, let me stress that these generators for the coproduct are of special type because the cation generators are primitive, whereas the Scholle generators are skew primitive, but even in a strong sense, because skew primitive means that comparing with a primitive element, you replace these ones with a group-like element. Now, this one is a group-like element indeed, just because HI is a primitive element. But here you have one, so you are replacing only one instance of one with something more general. And the same here for the EIs. So these elements are something intermediate between a primitive element and any skew primitive element. That's why I call them strongly skew primitive. Very good. That's your familiar.
And how do you prove uniqueness of such structure?
I lost the beginning of your question. Well, I mean,
how do you prove uniqueness?
Yeah. Okay. The structure is given by a coproduct. The coproduct is defined. In this case, you have something generated by generators and relations, and that's it.
So you just generators, you have it everywhere. I thought that you prove that there's a coproduct.
No, you have to prove the existence, actually, that these formulas make sense. Once they make sense, there is just one single coproduct. Okay, this is your simpler version of Drinfield's quantum algebra. You can also consider a, let me call, Drinfeld double version, where essentially you take a larger Cartan algebra, say twice as large, and then correspondingly, instead of a single set of simple coroots, you take two copies of each simple coroot. These two copies will enter in the description. How can I get rid of this stupid? I can't.
I don't know.
It was not there before. I don't know why. Well, here you have a positive and a negative version of the simple coroot. You'll have the positive version here, the positive version there. And in this commutation formula, where you have twice the simple coroot, the first one will be a positive simple coroot, and the second one will be a negative simple coroot. Well, so far, so good. Let me also mention that you have an alternative possibility. You know, the quantum universal enveloping algebra introduced by Jimbo and later used by Lustig and several other people. In this case, your ground ring is some field of rational functions on a parameter, the quantization parameter, which is now called Q. Good. Again, it is given by a presentation. Generators are generators of, say, Dural type and Scholle generators. And the relations are, say, close siblings to the relations we saw in the case of Drinfeld. Here you see, now the quantum relations look exactly the same, but the element is directly chosen inside the ground ring as being this power. Again, the key point is that onto this associative algebra, you can introduce a suitable coproduct, which is described in terms of generators by these formulas. And even in this case, besides this version of your Jimbo-Lustig quantum algebra, you can provide a Drinfeld double version, where again, the superscript D reminds me of Drinfeld double. Essentially, again, you take a twofold copy of the toral part. And in particular, these toral generators come in two different versions, a positive one and a negative one. So the positive copy will appear here in the coproduct for EI, and the negative copy will be used here in the coproduct for FI. So far, so good. Let me just also mention quickly the link between these two objects. I expect that if you are... Yeah.
May I interrupt for a second? This Drinfeld double construction is extremely important and extremely beautiful. I hope you agree. And if you start with, say, any finite dimensional Hopf algebra, then you end up, by taking the Drinfeld double, you end up with a Hopf algebra which is something like quasi or co-quasi triangular, right? So you have this additional structure, ribbon elements, and this is how I came to know it. But you see, I don't know if you are aware, we defined a skew version of it so that we have a Galois object over the Drinfeld double, yeah? So it is, and it's in this case it's isomorphic to the Drinfeld double, but there exists module present involution, like in Kohn-Moscovici, and they twist this Drinfeld double so badly that it's no longer a Hopf algebra, but it's a Galois object over this Hopf algebra.
Nice to know.
It's just a comment which you might.
Yeah. Okay. Of course, the theory is much richer than I can present here in a short while. Anyway, let's say if you are familiar with both kinds of quantum groups, you'll see through quite easily. If you're not, I doubt that a short comment will be enough, but still, I hope that it might be of some help. So let's say you have differences because we are taking algebras on different ground rings. And essentially, the connection here is that if you start with your quantization parameter being this h bar, then you can get your quantization parameter q just by taking an exponential. Conversely, if you are starting with the quantization parameter q, then you achieve a different deformation parameter h bar taking the logarithm. The same kind of relations takes place for the, let me call it, total part of your quantum group. And that's because, let's see it this way. In the polynomial algebra, you have these total generators, which generate some subalgebra, this curly K. Okay, now each one of these generators may be connected with a simple coroute via this kind of link. That is, I can see it as being the exponential of a simple coroute renormalized by the deformation parameter h bar. Conversely, if you start with these total generators of, say, polynomial type, you can recover the corresponding simple coroute via this formula. Notice that here, in principle, you get with this simple coroute, with their span, you get something which is contained in the Cartan subalgebra, but which might be smaller. That's why the definition of Drinfeld's algebra involving a choice of a Cartan subalgebra which is given from scratch is somehow more flexible than the definition by Jimbo and Lustig. Let me also mention that here, in a sense, you're passing from a vector space, say, to something which we might loosely describe as being its exponential. And then the exponential of a vector space, or rather of an abelian Lie algebra, is a torus. So geometrically, here there's some difference. Anyway, even if we ignore geometry and we think algebraically, with this kind of link, we might think everything is in quotes, so I'm slightly cheating, but we might identify our total part in the polynomial algebra as being a subalgebra sitting inside the total part of the formal algebra. In this way, all of my polynomial algebra embeds into the formal algebra. And conversely, the formal algebra can be seen as a suitable extension of the polynomial one, where the extension is achieved by enlarging the total part. So here I'm writing a tensor product over K, because inside here I already have the subalgebra K. The subalgebra K embeds into the total part of my formal algebra. If I pick such an extension, I end up, again, up to technicalities, with a larger formal quantum algebra. Everything here is given in the case of the, say, simple quantum algebras. You can provide a similar connection for the Drinfeld double versions of our quantum algebra as well. Great, so far so good, hopefully, for the case of uniparameter quantum groups. And now let's move to multiparameter quantum groups. When I say multiparameters, we have several parameters, but quite soon in the study of this theory, people realize that you can always, if necessary, rearrange, tune your description so that one parameter plays the role of a quantization parameter, whereas the other parameters have a different meaning. Essentially, they bear some geometric meaning. if you have one quantization parameter, then you can specialize, and so you forget that parameter, but you still have the other ones. After specializing, you get some Poisson structures on the semi-classical limit, such as a Licot bracket or a Poisson bracket, depending on what side of the geometry you are looking at. And then the additional parameters actually are responsible for describing this extra Poisson structure. So when saying multiparameter, keep in mind that there's a specific parameter playing the role of quantization parameter and the other ones having this geometrical meaning in a sense. Now let's look at these examples, these classes of multiparameter quantum algebras which were known in literature. I have to point out that for these examples, these additional parameters play very different roles in the two cases because essentially they affect the Hopf structure in quite different manners. Let's see it a bit in detail. We start with a first class of examples provided by Reshetigin. Let's say you start with some matrix psi, which only is required to be antisymmetric. And then out of this matrix, Reshetigin introduced a multiparameter quantum algebra of in the formal language, which as an algebra is exactly the same as Drinfeld's uniparametric algebra. So here you have no parameters whatsoever. On the other hand, on this algebra, he introduced a new different coproduct. And now the coproduct depends explicitly on the parameters, which are the entries of this matrix psi. In particular, if you are choosing your psi in the trivial way, because you are just taking zeros as parameters, then Reshetigin's algebra is exactly Drinfeld's uniparametric algebra. So it is included in this family. And also here I'm giving the notion for the simple version, but if you play the game with the Drinfeld double version, it still works fine as well. Great. This was a first class of example. A second class of example was considered by different people living in a different community, say. And I mentioned here Andruszkiewicz and Schneider as being the ones who gave the most important results in this theory, possibly. But there are several people working in this direction, say. In this case, you still start with some matrix where I put my parameters. The size is different now.
Not decipher who. Aha, it's at all. I thought it was AI. Okay.
No,
it's
no,
at all.
no, yeah, no. No. Luckily enough, there was no AI involved at this time. It was in the 90s.
AI, okay.
Yeah. Now, at this matrix, our requirement is that the entries have to match these conditions. So these are called Cartan condition because it depends on the Cartan matrix. And now, out of this matrix of parameters, a different multiparameter quantum algebra, now of polynomial nature, say, was defined, which now, as a coalgebra, is again a uniparametric algebra, namely Jimbo-Lustig polynomial quantum algebra in its Drinfeld version, Drinfeld double version, but still uniparametric. In particular, there is no role of the parameters here. On the other hand, this coalgebra now has a different algebraic structure, and for this different product, you have a role of the parameters. The product now depends on explicitly on the parameters. So as you see, it's an entirely different story compared with Reshetigin's family. Here again, there is a, say, standard case. The standard choice of parameters here is when you take as parameters Qij just these powers. So you have essentially just the quantum parameter Q, and you use it to introduce these extra parameters. But then the definition by Andruszkiewicz and Schneider is made in such a way that for this specific choice, what you get is simply the uniparametric algebra by Jimbo and Lustig, nothing new. So this in particular is again included in the family, in the multiparameter family. On the other hand, I also have to point out that this definition by Andruszkiewicz-Schneider is somehow intrinsically an object of Drinfeld double tap. Can always one could also cook up a version, a simple version, say, with Garcia. We did it, but it's somehow weird. It's problematic even to understand exactly what are you getting. So let me just say that in this context, the natural object really to look at is sort of a Drinfeld double quantum algebra. And actually, yeah, okay, that's enough for this, but let me point out the key point here. We introduced two different kind of examples, two different families of multiparametric algebras. The first one is given in the formal language, the second one in the polynomial language. However, this is not really the issue. The point is that the parameters play different roles. Essentially, as I mentioned, in the first case, by Reshetikhin, the parameters play a role here. They describe the co-algebraic structure. Whereas in the case of Andruszkiewicz-Schneider, they describe the algebraic structure. So it's not a matter of choosing different ground ring or different cartan parts. It's really a matter of the Hopf structure and the role of parameters in the Hopf structure. So this means that, at least apparently, there's no direct connection relating the two kinds of multiparameter objects as we had in the uniparametric case. Okay, so far so good, but I still need an additional tool, and this tool is given by deformation techniques in Hopf algebra theory. So that's a chapter of algebra theory. Let's say I have some Hopf algebra, possibly of exotic type in some nice tensor category. And then I consider the notions of twist and two cocycles. A twist is any element in my tensor square which satisfy these three conditions. I also have another notion that of a two cocycle. This is what? This is an element in the dual of the tensor square, which obeys these three conditions. Now you might see it directly if you are familiar enough. If you're not, let me tell you that these notions are perfectly dual to each other. What I mean by this? Well, you know that up to technicalities, Hopf algebras behave quite well with respect to linear duality. In that, if you take the linear dual of any Hopf algebra, this dual is on its own, again, a Hopf algebra. I repeat, up to technicalities, which might be even tricky, but still, when taken with a grain of salt, this statement makes sense. Well, in this spirit of linear duality, these two notions are perfectly dual to each other. Anyway, why should one be interested in twist and two cocycles? Well, the point is you use them to introduce deformations, which mean it's a recipe, a couple of recipes. Yep.
Yeah. If you allow me, so that people who are not eating Hopf algebras for breakfast every day, so that they realize issues with duality. You see, when you take a coalgebra and you dualize it, then it's immediately and obviously an algebra. There are no restrictions.
Yeah, the tricky point is the converse, clearly.
But when you have an algebra and you dualize it, well, it's a bit tricky to see that this is a coalgebra, and that's precisely because of using the algebraic tensor product to define comultiplication.
Yeah, and that's why you have to take tensor product as being something in principle more general than a sheer algebraic tensor product. And that's why you have to keep into account a more general notion of Hopf algebras. Depending on the context, Go ahead.
So the problem arises only in infinite dimensional cases, yes?
Of course.
Yes, of course. In finite dimensional, you have no problem whatsoever.
Yeah.
In infinite dimensional case, you have some problems, so you have to see how to handle this problem of let's say, the dual of a tensor product not being the same as the tensor product of the duals, unless you mean tensor product in some clever sense.
Okay, and also
that's
in the
the point.
graded case,
for instance, the graded
degree. is also fine, yes?
If the degrees are finite and you are taking, and if your product is graded, then you get rid of this kind of problems. But you see, depending on the situation, you have to look for the proper way to arrange to solve the issues. Huh?
Okay, thank you.
Good. Now, let's say we have these two kind of gadgets. I start with some Hopf algebra and I pick a twist F. Then I can do the following. I pick my H just as an algebra. I forget the coalgebraic structure. I keep the algebraic structure. And now I introduce this new map, delta sub F, which is the old coproduct delta, followed by a joint action by my twist. Then this turns out to be a new coassociative coproduct. So my H has a new coalgebraic structure, which also happens to be compatible with the old product. And so I end up with a new Hopf algebra structure, denoted in this way, which is the same algebra as before, but with a new coproduct, this one. And this is called the deformation of my H by the twist F. The dual recipe uses a two-co cycle. And now you are dualizing the story, so you are keeping your H just as a coalgebra. You forget the algebraic structure. You introduce a new coalgebraic algebraic structure because you look at this map, M sub sigma. Wait.
Yeah.
No, okay. How can I get rid of this stupid object? I can't. Okay. Yeah. This M sub sigma is M followed by a joint action by my sigma. Here, I mean a joint action with respect to the star, which is the convolution product. So you see the recipe is the same when read in a dual manner. So the point is, this map is a new associative multiplication, which means I have a new algebraic structure on H, again compatible with the old algebraic structure. And so I have, again, a new Hopf algebra structure, which is now new because what is new is the algebraic structure, the algebraic product. What it stands the same is the coalgebraic side. This is what we call deformation of H by the two-co cycle. Great, this works for any Hopf algebras with its twist and two-co cycles. What's the link with my multiparameter quantum algebras? Well, multiparameter quantum algebras are Hopf algebras anyway. So here is the link. In the example by Reshetikhin, we consider this kind of matrices, antisymmetric matrices, and Reshetikhin gave for each one of these matrices some multiparameter quantum algebra. But actually, you can use the same matrix to introduce a suitable twist for Drinfeld uniparametric quantum algebra. And once you have a twist, you can perform a deformation by twist. So this is the algebra obtained through the deformation process by twist from Drinfeld's uniparametric algebra. Here instead, you have Reshetikhin's formal multiparameter quantum algebra. The point is I have an equal in between. These two objects are the same. Actually, I'm cheating to stress the two different points of view. I'm cheating because this is indeed the way through which Reshetikhin defined his multiparameter quantum algebra. He defined this object on left-hand side as being given by the object on right-hand side. You also have a similar situation in the examples by Andruszkiewicz-Schneider. In that case, you start with a matrix of parameters of this type, obeying these conditions, and then using it, you have the multiparameter algebra by Andruszkiewicz-Schneider. But with the same lot of parameters, you can also define some two-co cycle for Gimbolustig uniparametric algebra. So now, with this uniparametric algebra and this two-co cycle, you perform a deformation process. And the point is, this deformed algebra is the same as Andruszkiewicz-Schneider algebra. So in a nutshell, what I have here is the following. Any multiparameter quantum algebra, either in the sense of Reshetikhin or in the class of examples by Andruszkiewicz-Schneider, can always be realized as a deformation of a uniparameter algebra. Drinfield's uniparameter algebra in the formal case, Chimbolustic uniparameter algebra in the polynomial case. So in this sense, both cases might be treated along the same pattern, but actually I'm cheating because I'm using the same word deformation here. But in the case of Reshetikhin, I'm taking deformations by twist. In the case of Andruszkiewicz-Schneider, I'm taking deformations by two cocycles, and the two are totally different beasts. So it's the same philosophy, but deformation has a dual nature, and so I'm still dealing with the different kinds of objects. Okay, before closing this, yep.
Very interesting. So am I right to interpret conceptually what you just stated here as follows, that no matter how you multi-parameter deform, there is kind of like one preferred parameter which cannot be erased. You cannot deform it in a way that this is not somehow a special case, right?
Yeah, you got it. The point is, I'm not sure. I don't know whether this is, say, something intrinsic to the theory, or it's just a matter of how we look at our objects. For instance, some of these multiparameter quantum groups, for sure, some examples of two-parameter quantum groups at the beginning were introduced with two or more parameters, let's say two parameters, which had exactly the same weight, the same role. But you could rearrange the description, changing using another pair of parameters. One of these is the ratio of the previous parameters, and the other is the product, say. And then the ratio can be used as a quantization parameter. And so in terms of the ratio, you have a quantum object, whereas the product of the parameters gives you a geometrical parameter, say.
Yeah. Very interesting.
Very good. Last word about this is that I wish to stress that these examples of multiparameter quantum algebras, both in Reshetikhin and in Schneider case, can always be realized as Drinfeld doubles. So you start with multiparameter quantum algebras of Borel type, you perform the construction of the canonical double, and you end up with our whole multiparameter quantum algebras. Anyway, that's enough. I spent a lot of time on the history before our contribution. So now it's time to talk about our contributions. Let's say we have now we begin. Yeah, in a sense. But I keep in mind the time passing by. So let's say we have a goal in mind. First, we are looking for a notion of multiparameter quantum algebra, which might extend both the examples by Drinfeld, by Reshetikhin, and the examples by Andruszkiewicz-Schneider. Also, let's say out of this, you see that essentially Reshetikhin's algebras can be achieved through a process of deformation by twist. And if you still perform deformation by twist, you still get objects of this type. So this family is stable under deformations by twist. And similarly, the family of multiparameter algebras by Andruszkiewicz-Schneider not only can be achieved from the uniparametric one through a process of deformation by two cocycle, but if you still go on performing deformations by two cocycle, you still get objects of the same type. So you have a stability under deformations, but now deformations by two cocycles. If we are looking, and possibly we find now, an object which is a generalization of both kinds of multiparameter algebra, then we wish also to have stability under both type of deformations. And the point is we succeeded, we get such a good notion. And also, this is a notion of quantum objects. If you specialize them, you get something semi-classical. Specifically, you get a lot of Lie bialgebras depending on multiparameters. So we find also a large family of multiparameter Lie bialgebras with nice properties and so on and so forth. Okay, so that's the sort of short summary of the situation. So let's start with an additional technical tool. We have fixed some Cartan datum from scratch. And now we move to a multiparametric setup. So I fix what will be my matrix of parameters, Pij. What I demand to them is to satisfy this condition, which is sort of a Cartan condition, which means that the symmetric part of P is fixed, must be the symmetrized Cartan matrix. What is freely chosen here is the antisymmetric part of P. We define a realization of such a matrix just by a straightforward extension of the notion of realization of a Cartan matrix, which is due to Victor Katz. So this realization is a triple, where the first entry is some free module of finite rank. The second is a set of elements in the dual of your H, which will be my set of simple roots. You also fix a set of simple coroots. Now there's nothing new. These simple coroots are twice as many as the simple roots. For each simple root, we have two different simple coroots. Well, different. They might even coincide, but a priori, you have a twofold set of simple coroots. Now, simple roots and simple coroots have to match nicely with respect to the parameters. Nicely means you require these conditions. In the case by Katz, you had, instead of Pij here, you had the entries of the symmetrized Cartan matrix. Okay, with some more technicalities, but not so many. You end with a nice notion, and you use it to cook up our definition of the main character of the story. So let's say we have fixed our Cartan data, we have chosen this matrix of parameters, and the realization. Then out of this, we introduce our formal multiparameter quantum algebra, this object, depending explicitly on P and on R, which is a unital associative algebra for which we provide a presentation. So the generators are exactly like for Drinfeld's algebra. The relations are essentially quite close siblings to the relations in Drinfeld's case. Where are some differences? Well, here you have hidden differences because in these coefficients, you have special values which are given by the parameters. So here, there are hidden inside the parameter. Here you have the simple coroots taking the place of the old coroots. But the more striking difference is here in quantum state relations because we have an additional coefficient. Also, this additional coefficient have two signs here because I took the blue plus when my generators are of type E, and I take the red minus when the generators are of type F. That is, I still have two sets of quantum cell relations, but now these relations are slightly different for the E's and for the F's. This part was concerning the word definition. But then I wrote also a theorem because there's something more which needs a proof. Something more is that you have a Hopf structure given by some coproduct, which in terms of the generators is given by these formulas. Let me stress that these formulas look exactly the same as in the case of Drinfeld's algebra. The Cartan generators are primitive, and the Chevalier generators are strongly skew primitive, with these Ti plus and Ti minus taking the role of the old simple coroots. Great. As a root theorem, there's something which needs to be proven. We provided several proofs. The first proof is simply, okay, take the standard case by Drinfeld. Even there, you have to prove that the coproduct is well-defined and has the right properties of a coproduct. Take a usual proof, like in, for instance, the book by Charlie and Presley, and try and test those arguments and computations in our present case. And it works. So you can follow this strategy. Another possibility is the following. If you read my definition, it looks like it's some multiparameter quantum algebra where the parameters are ruling the algebraic structure, whereas the coalgebraic structure is independent of parameters. This is exactly what happened with the multiparameter quantum algebras by Andruszkiewicz and Schneider. However, the point is, Andruszkiewicz and Schneider algebras were of polynomial type. So what we need here is to have a sort of formal version of Andrews-Schneider algebra. The point is, yes, you can do that. You take Andrews-Schneider algebra, which is polynomial, and you extend the toral part by extending the toral part by scalar extension in quotes, just like we found in the uniparametric case. What you get is a larger algebra. Here in the polynomial side, you had a presentation. Through this construction, you get a presentation for this larger algebra, and you find that it is exactly the presentation that I wrote in definition 1. Even more, here in the polynomial algebra, you have also coproduct. From the presentation, this coproduct has a unique way to extend canonically to the larger algebra. So this larger algebra also inherits from the polynomial mother, say, it also inherits a coalgebraic structure. And that's it. So the idea is, let's construct my formal multiparameter quantum algebra as a formal version of the polynomial 1 by Andrews-Schneider. Third and fourth proof are essentially an incarnation in this multiparameter setting of strategies that one can follow typically in the uniparametric setting. So the third case, you construct your object as a Drinfeld double. In the fourth case, you construct it as a double cross product. In both cases, the point is you take a tensor product and you wish to endow it with some Hopf algebraic structure. The tensor product in both cases is made out of a pair of Borel objects. So in both cases, you start constructing multiparameter quantum algebras of Borel type, a positive one and a negative one. Okay, you need to describe them, so they are not given from scratch, so there's something to prove, but it's easier. Then, in this first case, you provide also a pairing. And then, out of the pairing, the canonical recipe of Drinfeld double provides you with a Hopf structure on this tensor product. The construction gives you also a presentation, and you realize that the presentation is the one we have in definition 1. So we got a proof via a concrete construction. This is sort of an alternative argument because you still start constructing Borel type multiparameter quantum algebras. Now you need to provide a suitable action and coaction of each one of these Borel objects onto the other. When you have all this data, you can introduce with a canonical recipe a suitable Hopf algebra structure on this tensor product. And this structure now also inherits an explicit description, which is again the one in my definition. The fifth proof is really, say, different in spirit because it follows a different path. It is this kind of construction. Let's say we already have quantum groups of depending on one parameter. So uniparametric quantized universal enveloping algebras. Then, if we deform them and we introduce parameters in the gadget that you use for deforming, you'll end up with multiparameter quantized universal enveloping algebras. So you can do that directly by 2 cocycle, and you end up with something which has exactly the description of the kind I have in my definition 1. So at least some of my multiparameter quantum algebras can be achieved via a deformation process by 2 cocycle. Then you see that choosing carefully the 2 cocycle, you can get any possible multiparameter quantum algebras. There is also a more striking fact, that is, the same method works if you perform deformations by twist. At first sight, this will not give you something of the kind you're looking for, but with an additional piece of work, you get exactly a multiparameter quantum algebra as in my definition. I'll be back in a moment on this, but for the time being, let me say that whatever your preferred method, we did prove that these algebras of ours to admit a whole Hopf algebraic structure. So they are quantum groups in the sense of being Hopf algebras with their whole structure. Great. So now I have this large family of multiparameter quantized universal enveloping algebras with several nice properties. For instance, you have a property like triangular decomposition property. And here we are very proud. We found a new, totally original proof of the triangular decomposition property, which is totally independent of all proofs you can find in literature for quantum groups or for classical universal enveloping Lie algebras. Very nice. But the feature that we consider most striking for this family of objects is the stability by deformations, which was one of the goals we had in mind. So let's see what happens here. Okay, we have a general theory of deformations by twist and by two cocycles. The Hopf algebras we have in mind that we want to deform now are our multiparameter quantum algebras, but we fix a special subclass of twist and of two cocycles that we name toral. What is a toral twist? Well, let's look at this sum. This is just a single tensor of rank 2 for the Cartan subalgebra. If you choose these coefficients to be to form an antisymmetric matrix, is here, then your tensor is a skew-symmetric tensor. You put your quantization parameter in front of this tensor, you take the exponential. Now this object is something living in the tensor square of your multiparameter quantum algebra.
Sorry, just a quick question.
Yeah.
This H should have one or two subscripts, since you have written K and G.
Yeah. So I have it in the first level. Oh, yeah. Okay. That's so you see, Piotr, here is the first misprint.
I told you it's inevitable. I mean, it's impossible.
Yeah. Okay.
Perfectly.
No, here I'm taking a basis, so you have just one single index.
AG. Okay.
Okay. Okay. The basis is just to write down a tensor using the basis.
Sure.
And so you describe it through a matrix. Good. Anyway, the point is, since the elements in the Cartan subalgebra are always primitive, such an element is automatically a twist. Good. So I have this large family of twists that I call toral twist. The definition of a toral two-cocycle is quite a bit more tricky. Okay, you start with something dual, that is an element in the dual of the wedge product of H with itself. Good. Also, you need to require this condition. This condition is the one which ensures you that you can extend this chi to a two-cocycle of my formal multiparameter matrix. But that's not yet enough. Now with this two-cocycle, chi, you consider this exponential. Now, here I'm saying exponential. Exponential needs power, so a product. Here, the product involved for chi is the convolution product. Okay, so this makes sense. But there's something weird, which is this h to the minus 1. A priori, this makes no sense whatsoever. Nevertheless, if you take this formal object, you can realize by concrete analysis that this formula does gives you a well-defined map which has all the properties of a two-cocycle for this algebra, for this Hopf algebra. What's new is that this two-cocycle a priori has values in this larger ring. Actually, you do not really need all the field of Laurent series. You need much less. But still, what's relevant is that the object makes sense. It has the properties of a two-cocycle, so you can use it to perform the construction of a deformation by two-cocycle. A priori, this deformation will give you a Hopf algebra with coefficients in this larger ring. But looking carefully at the result, at the deformed product, you'll find that this is not indeed necessary. you end up with a deformation which still takes place on the old ground ring of formal series. By the way, you see this entirely by hands via a careful analysis of what is the meaning of this object, which does not come out of the blue, but that's another story. However, there's something much more interesting going on underneath. That is, this is just one instance of a phenomenon more general that we studied in detail. There's also a dual counterpart for twists, but that's the content of a different paper. It's a matter for another talk. For the time being, let's say one just see by hands that this works. Good. So what's the point here? With this total twist and total Tuchel cycle, we do get a stability result, which goes as follows. I wrote the statement in a way, but I will now read it to you in a different way. Let's say I'm starting with some, yeah.
What is stable? What do you actually mean by stability?
Yeah, here it is. Here it is. Let's say I take an element in my family of multiparameter quantum algebras, and I perform a deformation by a total twist. Or here on the right-hand side, I perform a deformation by a total Tuchel cycle. A priori, the outcome will be some Hopf algebra. However, this outcome is not anything. It is again an object in the same family. It is again a formal multiparameter quantum algebra. Even more, I do know exactly which one, because I know exactly what is the new matrix of parameters and what is the new realization for this matrix of parameters. And here as well, I have not only a new Hopf algebra, but one which is described according to my definition for a different matrix of parameters, which I do know explicitly, I can compute it, and a new realization explicitly known for this new matrix of parameters.
So can I say that it is invariant under twisting?
Yeah, invariant under deformations. And it's not only that you still are inside, you do know exactly what the result looks like, which means that you can read this, say, equality as an equation. You might say, let's say I have here some fixed, and here as well I have something fixed. Can I find a suitable twist which leads me from this to this? In other words, you have an action of total twist, which form a group, and an action of total Tuchel cycles. This action is, under mild assumptions, this action is transitive.
Exactly, yes, now I understand.
And in particular, under this transitive action, please remind that we have a special point, which are the standard multiparameter algebras, the ones where the choice of parameters is trivial. Essentially, uniparametric objects. Riemann algebra. And so this means that
is this action free, or do you have some fixed points that you act with your twist, but it's an isomorphic Hopf algebra?
We didn't look into it. I think you in principle have some kernel. You can compute it if you want, because everything is pretty explicit. So this means I have stability under total deformations in both cases, and even more. It's more precise than that, so we'll have some further consequences. Let me spend a word here on the proof, because here is where really there's something, say, surprising going on, which in particular needed a clever idea. I have here two results concerning deformations by twist and deformations by Tuchel cycles. Let me look here. Here you start with our formal multiparameter algebra. Here the parameters just rule the algebraic structure. They live in the algebraic side. They do not live in the coalgebraic side. And you are performing a deformation by Tuchel cycle. So you are modifying the algebraic structure, but you are not touching the coalgebraic structure. So at least the outcome will be again a Hopf algebra whose coalgebraic structure is independent of parameters. It's the same as before. And you had parameters involved in the algebraic structure. So at least the outcome looks like a formal multiparameter algebra in our sense. So the point in this case is just that you have to now read carefully the outcome after performing computations. You have an Hopf algebra where the coalgebraic structure stands constant, and the algebraic structure depends on parameters, the old parameters plus the ones coming from the two cocycles. You read carefully the new algebraic structures. In particular, you read carefully the new relations, and you find out that they are again relations coming from some new matrix of parameters and some new realizations. You still end up with something in the family of multiparameter quantum algebras. Let me point out that here, in this case, the realization changes in this way. The Cartan subalgebra stands the same. You still have the same set of simple coroots, essentially because the simple coroots gives you the coproduct of Chevalier generators, and you're not changing the coproducts. What you are changing, indeed, is the set of simple roots. Simple roots enter in one set of commutation relations, Cartan generators with Chevalier generators. You are changing the product, so you are changing those relations, which means you are changing the values of your simple roots. You're taking a different choice of simple roots. In the case of a twist, instead, what you are changing is just the set of simple coroots, and we'll see how this happens. So this was to say that the result concerning Porter two cocycles, in a sense, it's a matter of computation, but it's not surprising. What is really surprising is what happens with twists. And here it goes this way. Let's say you have your formal multiparameter quantum. You perform a deformation by a total twist. It's a deformation by twist, so you're getting the same algebra. So this is the same algebra as you started with, so it has the same presentation with the same generators, the same relations. Now let's look at these generators for the coproduct. For the old coproduct, they were primitive or strongly screw primitive. For instance, for generators of type E, this was the formula. But now we have, after the deformation, we have a new coproduct. Now, with the new coproduct, the computations gives you such a formula. These curly AHR elements in the Cartan subalgebra that I do know explicitly. So this is a group-like element. This is a group-like element. My EIs are again screw primitive, but no longer strongly screw primitive. However, this is not such a great issue. With a slight reformulation, you renormalize a bit your Chevalier generators. You take this one. And now this one is strongly screw primitive. And you see in the part which is not 1, this is an element in the Cartan subalgebra, so this is a group-like element. And you know it explicitly. You have a formula for it. What is this? Well, this will be our new simple coroot, because it is the one which describes your coproduct, your new coproduct on the ith Chevalier generators. This is the story for generators of type EI. For generators of type F, that's the same story. Your Fi is no longer strongly screw primitive, but it is screw primitive. If you modify it in this way, this curly G is again something in the Cartan subalgebra that you know explicitly. With this modification, you get a new element of Chevalier type, which is strongly screw primitive. This will be my new simple coroot of negative type. Finally, with the Cartan generators, there's no problem because they still are primitive. And so at the end of the day, I have replaced my original generators with these new elements, which it's immediate to see they still generate my algebra. Okay, so I have a new set of generators, which now are better than before because for the new coproduct, they have the right behavior. They are primitive, the Cartan ones, and strongly screw primitive. And in the formula for the coproducts, we also see directly what should be or what happened to be the new simple coroots. Great. Now, with these new generators, I have a new presentation. The generators are not that far from the original ones, so it's not only possible, but it's even easy to write down out of the old relations for the old generators. You can write down explicitly the new relations for the new generators. So you end up with a different presentations where you have these new generators and you explicitly have the corresponding relations. Now you read these relations. You hope that there'll be relations of the kind that you find in the description of some formal multiparameter quantum algebras. If there is a proper matrix of parameters which fits with these relations. And then essentially out of the relations, you read the correct parameters that are playing this role. So really after a change of presentation, you find a new parameter, a new set of parameters forming this matrix, and a new realization, essentially the change of simple co-roots, which tells you that your object actually has a presentation of the kind that we need to define multiparameter quantum algebras. You had not it automatically just by taking the original presentation and seeing what changes when you perform the deformation. You have to change the original presentation. So at the end of the day, we get such an isomorphism, just sending the abstract generators here in these new generators that I found myself. In this way, you essentially perform a clever change of presentations for the deformed algebra. Change of presentation that in the end boils down to a simple, slight renormalization of the Chevrolet generators together with a change of the simple co-roots. That's where we really need a clever idea, which, by the way, was due to my colleague Garcia. Okay, a couple of remarks. Well, the first one, essentially, I already mentioned it. The second one is what we were saying before, that is, with very mild assumptions on the realization, essentially the Cartan subalgebra should not be too small. Whatever formal multiparameter algebra you have in mind, you can always achieve it starting from a standard one, which means essentially from Drinford's uniparametric algebra, using either a tooth co-cycle deformation or a twist deformation. The point is you have to, depending on the choice of P and R, you have to choose carefully your total two co-cycle or your total twist. Very good. Essentially, I think, yeah, we can recap all these graphically. Say, we start from a uniparametric quantum object, Riemann algebra, and then you can perform deformations by total two co-cycles or total twist or total two co-cycles. Okay, now what I mentioned is that in both cases, you get a formal multiparameter quantum algebra, but I wrote exactly the same formal multiparameter quantum algebra. And that's because if you decide to achieve this object, then you can choose the total twist or the total two co-cycle to get the same. However, this looks a bit weird because the two objects here on the left and on the right, why doesn't this work? We don't know. Yep. Here on the left, you have an object where you have parameters coming from phi, from the total twist, but these parameters affect the coproduct. Here instead, you have parameters coming from your two co-cycles, which are ruling the product. You see them in the multiplicative structure. So these two objects apparently are of totally different nature. The point in the proof of my theorem for the twist side of the statement is that you actually have an isomorphism between these two kinds of objects, which at the end of the day boils down to choose a carefully selected change of generators. Great, I think that's essentially enough for the story concerning the quantum level. Now, a bit more quickly, I will mention what happens at the semi-classical level. Yep.
Can you go to the slide for just a second?
Yep.
So you have this kind of duality here between F phi and the sigma chi, right? You mentioned some duality. And this duality you also have between the red and the blue here, right?
Yeah.
Okay.
Yeah, but wait, the notions of twist and two cocycles are definitely dual to each other. You are acting in dual manners. Here you are deforming the coalgebraic structure. Here you are deforming the algebraic structure. That's why it seems impossible to somehow correlate the two sides.
I understand that
Let,
quite surprising, but
but wait a moment. Yeah, let's say we found an isomorphism directly by hands. You can get the same isomorphism at the level of Borel multiparameter quantum algebra. If you replace this G by a Borel B plus or B minus, you have the same kind of situation. Right? Via the same change of generators. You just renormalize the Chevalier generators. Now, I think that the key point is that this kind of quantum algebras, Borel quantum algebras, starting with Drinfeld ones, are essentially self-dual. And my quantum G is a Drinfeld double, so it's almost self-dual. So at the end of the day, I mean, we have a proof by direct computation, but I think that the true reason underneath is that we are working with some quantum objects which have a self-dual nature.
Yeah, I like this. Yeah, I like that.
That should be the real. We are working on a general theory about that, and from there you should see that this works exactly when you're starting with something which is intrinsically self-dual, and then you have this kind of identifications of two apparently totally different deformation techniques. Good. I can be more quick on the semi-classical side. Let's say we want to play the same game. So you start with the same combinatorial data, a Cartan datum, a matrix of parameters associated with this Cartan matrix, and a realization just as before. And now we introduce, instead of a multiparameter quantum algebra, we introduce a multiparameter Lie algebra. Again, by a presentation with generators and relations, we give you the Lie algebraic structure. The generators are exactly as in the quantum case. The relations are essentially relations like in the description of a Kac-Moody algebra, if you want. Good. Now, this is the definition side of the story. I wrote theorem because you have more, as you can guess. What you have more is that on this Lie algebra, you can introduce an additional structure, namely a Lyko bracket. This Lyko bracket is defined on generators in this way. And then it is compatible with the Lie bracket. So at the end, you have a Lie bialgebra structure, which is multiparametric because it depends on parameters hidden inside here. Here you do not see them explicitly, but in these values of the half of the simple roots, you also have a role of the parameters. Great. Again, there's a theorem, so you have to prove something. Let me say we gave 4 proofs. These 3 proofs are just, if you want, semi-classical counterparts of similar proofs that I mentioned in the quantum case. These first 2 proofs uses construction of mining double or construction of double cross sum. The first one is the counterpart in the setup of Lie bialgebra theory of the construction of Drinfeld double. And here is the classical counterpart of the construction of double cross product for Hopf algebras, which now is replaced by a double cross sum for Lie bialgebras. Of course, there's some work to be done. First of all, you have to construct your multiparameter Lie bialgebra of Borel type, but this first step is easier, and then you pass through this canonical construction of Manning's double or double cross sum. By the way, all these constructions are totally, I mean, now I presenting them after the quantum constructions, so you think as being inspired by that, but they are totally independent, presented in the paper totally in an independent way. You can also provide a construction through a deformation process, so you start from the standard Lie bialgebra where there are no parameters, but there is a a Lie algebra structure, essentially Kirillov constant Lie co-bracket on a Kac-Moody Lie algebra. Then you perform a deformation, and what you get is something which matches the definition of multiparameter Lie algebra. The fourth proof instead is of different nature. Namely, you say, okay, I want to introduce some Lie algebra structure on this object. Good. Then with P and R, instead of constructing directly this object, I consider the formal multiparameter quantum algebra associated with this P and this R. Okay, that's a quantum object. I specialize it for H equal to 0. What I get is the universal enveloping algebra of some Lie algebra. You have a concrete description for this. You get a concrete description for the limit Lie algebra. And this gives you exactly an object like in the definition of multiparameter Lie algebra. Let me say cast this last argument in this fourth proof as an independent statement. What I'm saying is that if you take a multiparameter quantum algebra of our family, then its semi-classical limit is a multiparameter Lie algebra in the sense of the definition that I just gave. Or to put it the other way around, if you look at some multiparameter Lie algebra following my definition, then for this we have at least one quantization, namely the multiparameter quantum algebra associated with the same P and the same R. That's once you have the definition. This is just reading through the description of these two objects. Great. What's the interest in this family? Okay, there are other reasons of interest, but now let me just stress the fact that this family is also stable by deformations, where we mean deformations here in the sense of Lie algebra theory. For Lie algebras, you also have a theory of deformations by twist and by two cocycles. Okay, you have technical definitions. A twist is an element in the tensor square obeying these conditions. A two cocycle is just a dual notion. You take something, a dual of the tensor square, which has to obey these conditions. And then you use these gadgets to introduce deformations. So you can start with some Lie algebra and the twist. And so you use the twist to define a new Lie co-bracket. This new Lie co-bracket is again compatible with the old Lie bracket. So the old Lie algebra structure and this new Lie co-bracket gives you a new Lie algebra structure. This is the deformation by twist. The dual recipe takes your G and the two cocycle gamma. You use the two cocycle to define a new map, which happens to be a new Lie bracket. Now this new Lie bracket, together with the old Lie co-bracket, makes your G into a different Lie algebra. Only partially different, because what's new is just the Lie algebraic side. This is your deformation of G by the two cocycle gamma. Now, in my family of multiparameters Lie algebras, I'm now focusing on twist and two cocycles of toral type. The definition now is easier. Simply for the twist, you take just any antisymmetric tensor, and this antisymmetric tensor is automatically a twist. We call all of these toral twists. In the dual setup, you take any element in the dual of the wedge, just obeying these conditions. These conditions ensures that you can extend this chi to a map over the tensor square of my multiparameter Lie algebra, and this will be automatically a toral two cocycle. Now the stability result reads as follows. You start with some multiparameter Lie algebra, and you consider a deformation by a toral twist or by a toral two cocycle. A priori, you get some Lie algebra. The point is you describe it explicitly, and you find that it is again a Lie algebra in this family. Namely, it's a multiparameter Lie algebra associated with some new matrix and some new realization in both cases. But notice that here I'm writing P phi and R phi, which is exactly the same notation as in theorem 2, because I'm getting the same matrix of parameters and the same realization as before. Again, you just perform your process of deformation and you read out the results. In this case, the situation, well, for the deformation by Tuco cycle is essentially the same spirit. In the case of twist, you have a two-step process because you perform the deformation, then you have to change the presentation. But the change of presentation in this case is quite simple. Essentially, you just have to change the choice of simple co-roots and nothing more. So it's definitely much easier in this case, the result. In any case, your family of multiparameter Lie algebras happen to be stable by both kinds of toral deformations. To finish with this stuff, I will summarize graphically the relationship between the two levels. Here on top line, I have quantum objects and deformations among them. On the bottom line, I have Lie algebras and deformations. On the left, I have deformations by Tuco cycles in both senses. And on the right, deformations by toral Tuco cycles. What I said here, Tuco cycles, no, these are toral twists. Okay, now for the objects concerned here, we saw some result. Theorem 2 tells us what is the result of performing toral deformations on quantum objects. Theorem 5, the last one, tells us a similar result for deformations of multiparameter Lie algebras. And theorem 4 connects the, say, top level with the bottom level because it tells us if we are specializing a quantum multiparameter objects, what I get is a classical multiparameter objects with the same multiparameters involved and the same realization. Now, if you take all of this together, at the end of the day, what's going on here is that if you perform a deformation at the quantum level, say here by toral twist, and then you follow with a specialization, then that's the same that starting with a specialization and then performing the toral twist deformation where the toral twist is given by the same phi that you have here on top. In other words, this diagram is commutative. The square is commutative. And similarly here on the right-hand side. In a nutshell, let me say, the point is, for this kind of deformations, the specialization process commutes with the deformations by toral Tuco cycles, and similarly, it commutes with the deformations by toral twists. Very good. So this was essentially all what we did with Gaston Garcia. Just a couple of words on what's happened later in the last year, essentially. The first step was a joint work by the three of us, Gaston, myself, and Paolini. Essentially, what I told you so far was concerning some symmetrizable Kac-Moody Lie algebras and their quantum counterparts. We constructed multiparameter versions and so on and so forth. Well, you can play the same game by replacing these symmetrizable Kac-Moody Lie algebras with simple contragradient Lie superalgebras. So you have Lie super bialgebras, Lie Hopf superalgebras involved, and so on and so forth. You know, these Lie superalgebras, those that in a classification by Katz are labeled by types A through G. So they are given by thinking diagrams and so on and so forth. So this means that we find a large family of multiparameter quantized universal enveloping superalgebras. This family is stable under deformations by toral twist and toral Tuco cycles and so on and so forth. And also we have a semi-classical counterpart providing a huge family of multiparametrically super bialgebras, stable deformations, and so on and so forth. Let me stress that for the quantum setup, there were no examples previously known, such as the families of examples by Reshetygin or those by Andruszkiewicz and Schneider in the non-super setup. So we had to resort mainly, almost only, on the method by deformation. So we started with a uniparametric object, which is a formal quantized universal enveloping superalgebra introduced by Yamane. This is just a, say, super version of Greenfeld's quantum algebra. For this object, which is uniparametric, we perform deformations by toral two-cycle or toral twist. And the objects we get will have a specific description. This will give us the very notion of formal multiparameter quantum algebra. And then for this family, we prove stability under deformations and so on and so forth. For the semi-classical side, the situation is in a sense entirely similar to what we did in the non-super case, because also in the non-super case for Lie superalgebras, there were no examples to base upon for our multiparametric construction. And finally, the last contribution, finished it in December, 1 month ago, by Paolini and myself. In this case, we focused on the general linear supergroup. So for this general linear supergroup, we have in particular a formal quantum multiparametric superalgebra, as we constructed with Garcia. But now we are looking in a dual manner. That is, we are taking, instead of looking at this quantized universal enveloping algebra, we're looking at its dual, which is, in Greenfeld language, a quantum formal series of superalgebra. Essentially, a quantization of the function algebra over a formal supergroup associated with your Lie superalgebra. Good. Now, what's the point? For this object, namely for this one, the dual of this quantum algebra, this is the quantum superalgebra that we considered with Garcia. We studied its dual, and for this we found a complete explicit description by generators and relations that we found in two different ways of this dual, and also a description of its pairing with the original quantum universal enveloping algebra. Here I also only want to mention that in the presentation, the generators are the most natural ones. That is, you look at this generally linear Lie superalgebra. It has, just like the general linear Lie algebra, it has a natural representation. This natural representation have some matrix coefficients. By general theory, these matrix coefficients will generate this whole object. And then, starting from these objects, we find a total description of this object in two ways, as I said. One is by hands, in a sense, and the other one is through a deformation argument. And finally, I just mentioned that a similar object was introduced and studied by Mani with an entirely different point of view. It was produced as an FRT construction. And but at some point, he considered a slightly different superstructure, I mean a different supergrading, so that in the end, his object is intrinsically different from ours. So, okay, we still might make a comparison, but we cannot expect the two of them to be the same. And I think that's it. Thank you for your attention. I just give you here a list of references for further readings if anyone is interested in it. That's it. Thank you very much.
Grazie mille. Grazie mille.
Thank you.
Please notice that I kept the time.
Oh, yeah, I noticed you finished like 2 minutes too early. Okay, perfect. C'è una domanda.
You'll discuss. Okay, go ahead.
Any questions?
Yep.
Adam, Tomek?
Oh, I'm happy. Very nice talk. Thank you.
Welcome.
Tomek?
This was not a question.
Exactly. It was a comment.
I have maybe two questions.
Okay, go. Tomek again. Okay, first
So,
Tomek.
Yeah. So since in many of examples, you see that different deformations, even given by two different methods, dual one to each other, can produce the same by algebra or Hopf algebra. So my question is, how big part of the Gersten-Haber-Schach deformation theory is covered by your combination of your twists and two-cycle deformations?
Well, let's say
Because
yeah. I have the impression that the Gerstenhaber theory is, in a sense, is independent of the story of deformations by twist or by two co-cycles. Of course, you can have a connection between, because when you take a twist which contains some deformation parameters, such as this H bar, then you introduce a new coproduct, which is depending on this parameter. And so it is a deformation which might be cast in the language of Gerstenhaber. Maybe I'd be more familiar looking at the deformation of the multiplication, so looking at deformation by two co-cycles. However, one should see whether Gerstenhaber theory might help me in deduce the behavior of a deformation by twist from the twist itself, from scratch. I'm not sure this is feasible.
So the Gerstenhaber shock deformations are, in fact, deformations up to isomorphism. It's a cosmology theory behind this, and this is about all possible deformation.
All possible deformations.
Multiplication, co-multiplication, and both together. So these are the most general deformations. And,
let's say,
it's well known that this idea of twists and two co-cycles in this Andruszkiewicz and other cases, they are in fact the only one cases when you can prove that the image of your deformation in this universal Gerstenhaber shock theory is non-trivial. But I wonder how big part of universal deformation is covered by these twists and two co-cycles. So in your theorem number 2 and number 5 in this quasi-classical case, you see that different deformations produce the same Hopf algebra. So it's not clear to me how much non-trivial they are. How
I
much
might have a partial
are.
answer. I might have a partial answer, which is as follows. Let's say let's go here. As I said, one consequence of this kind of result is that the same kind of object, my multiparameter Lie algebra, can be described actually in two different ways. If you want, the way arising from deformations by two co-cycles means that you have parameters occurring in the Lie algebraic structure, whereas the Lie coalgebraic structure is constant; it's independent of parameters. And if if you prefer to think in Hopf algebraic terms, that's for deformation by two co-cycles of Hopf algebra. Good. If you perform deformations by twist, you are introducing parameters in the Lie co-bracket, in the Lie coalgebraic structure. Okay. Now, at some point, so if you want, Reshetkin was studying deformations of one kind, Andruszkiewicz Schneider were studying deformations of the other kind. But at the end of the day, due to this kind of theorem, you can decide to describe your objects in either way. So we decided to give our notion of multiparametric objects, the quantum ones or the Lie bialgebraic ones, with a presentation where the parameters are given in the algebraic side. But you might introduce a different definition where you have a multiparameter object, where the multiparameters only rule the co-side, say the coalgebraic side. Okay? Apparently, these are different theories. This theorem tells you that you have the same theory, The reason is that we have this isomorphism which comes out of a self-duality of Borel objects, in a sense. So this is not something which might hold in total generality. At the end of the day, I'm constructing something of the type Drinfeld double of Borel objects. Now, what I'm willing to say here is that we decided to choose the description with parameters in the algebraic side. But let's say you choose the description with parameters in the Lie algebraic side. So for instance, you have a fixed Lie algebra and different Lie brackets. That's exactly what you do when you are studying Poisson structures on a semi-simple algebraic group or a semi-simple Lie group. Infinitesimally, your Poisson structure is given by a Lie bracket on the tangent Lie algebra. Is it clear? Yeah. So yeah. The Poisson group is always the same as an algebraic group or as a Lie group. So you always have the same tangent Lie algebra. What you are changing with the Poisson structure is the Lie bracket. Now, in the classification of Poisson structures on your given Lie group actually boils down essentially, at least infinitesimally speaking, to the classification of Lie brackets compatible with the given Lie algebra structure on your tangent Lie algebra, which is a semi-simple Lie algebra. Good. Now, these Lie brackets were classified at some point, and the point is you have, I don't know exactly the statement, but the key point is you have a large family of Lie brackets, Lie brackets on this semi-simple Lie algebra, which is parameterized by antisymmetric tensors, and which is exactly the same family of Lie brackets that you find through deformations by toral twist. So with this strategy, with this method of deformations by toral twist, we are getting almost all structures, in the sense that we get all the structures or the Lie brackets in this large family, which is large because it is dense in the whole family of all possible Lie bracket structures on the given Lie algebra structure. So if the question was,
what is your category in which you are considering equivalence or isomorphism? So it is what? It is Hopf algebra with somehow distinguished pair of
now
Borel substructures.
In this case, I'm talking of Lie algebra structures on a given Lie algebra. So you have a semi-simple Lie algebra, and for this one, you consider the moduli space of all possible Lie bracket compatible with the given Lie algebra structure.
So you are fixing.
You have fixed the Lie algebraic structure, and you are considering the possible Lie brackets, which means you are fixing your Lie group, a semi-simple Lie group, and you are looking for all possible Poisson structures on it. There is some classification result, and in particular, the classification you have this large family, which is large in the sense that it is dense in the moduli space of all possible Lie bracket structures. The same family can be achieved through deformations by toral twist. So in this sense, this is an answer. That is, with toral twist, you achieve at least all this dense family, which is, in a sense, it's almost all of the structures. That's the best I can give you as an answer. I'm not especially expert in Poisson geometry. I'm not an expert of anything at all in general. Still.
Yeah. So I wonder: is there some cohomology theory, some analog of Gersten-Haber-Schach theory for your kind of rigidified situation? Because then you could formulate some theorems that, for instance, that your deformations are dense in some universal class of deformations of some type.
Well, as I said, as I said, I have this idea, but I never took time to check it. But here the point is really that we, instead of working with this G, we might work with the Borel subalgebra. And as I said, the key point with this Borel subalgebra is that when you look at its, you take the standard Lie bialgebra structure. So you have the Lie algebra structure and the Lie co-bracket, I think it's all Kirillov constant Lie co-bracket. So the formula is this one. So imagine you have, okay, instead of taking a presentation of G, here I'm taking a presentation, the usual presentation of a Borel algebra associated with some Cartan algebra. Okay? So you have only generators of type E, you have simple co-roots, simple roots. Good. And the set relations. And then you have a Lie bialgebra structure, which is trivial on the Cartan subalgebra, and on the Chevalier generators has this form. Here, instead of Ti, you should read Di times the simple co-root Hi. Good. That's a possible, the most famous non-trivial Lie bialgebra structure on your Borel algebras. Well, now you have a Borel algebra of positive type, you have a Borel algebra of negative type. Both are given a Lie bialgebra structure, but now with this Lie bialgebra structure, these Borel algebras are dual to each other. And then, even more, saying positive or negative, it's almost just a matter of terminology, of notation. At the end of the day, your Borel algebra, either positive or negative, is self-dual as a Lie bialgebra. And I think that now the point is, when I perform a deformation by twist, I'm doing some techniques. If I perform deformation by two-cycle, I'm taking the dual construction. But if my initial Lie bialgebra is self-dual, when I perform a dual construction, it's like doing the original construction on the original object. So once stated properly, this should be the key, that I'm working with self-dual objects. And that's why two dual techniques at the end give you the same result. So it's not a matter of general cohomological property. It's a matter that I'm actually working with some special objects which have this self-dual property.
Yeah, and there is a theorem that these twists or cocycles generate all such possible deformations, preserving this more rigid structure, or not?
Say it again. You want a theorem?
So is it true that is there behind this result some theorem that if you have this rigid self-dual structure, then the only kind of a deformation is either...
I see. Well, I'm guessing something similar. We are now developing a general theory of Lie algebras, actually Lie super bialgebras, where this theory of toral deformations by toral twist and toral two-cycle should work nicely. Well, actually do work nicely. There's plenty of examples falling within this notion, so it seems to be a meaningful theory. And in this context, your question becomes sort of a conjecture. It's my task in these very days, so I'm free to work on it, to state precisely what you are suggesting, and then there should be also a more or less direct proof. In the sense that if you have a self-dual object, then applying dual constructions will give you the same result, essentially.
Yeah, it would be very nice result.
This should be the real theoretical explanation.
Yes. Thank you very much. Thank you.
Well, you're welcome. It's a pleasure.
Yeah, go ahead.
Hello, thank you for the talk. I wanted to ask about the Hopf algebraic part, and maybe first you mentioned the Borel object. Is it simply defined by taking part of the generators?
Yeah. If you want a definition, you take the definition. Here it is. You take just, for instance, the generators of type EI and the corresponding relations. Oh,
Okay,
the EI and the Cartan generators, of course.
If I remember correctly, at least in the Drinfeld-Jimbo case, this Borel algebra also can be realized via bosonization. Is it the same here?
Yeah, it is. Yeah, it is. You know, Garcia is an expert of this story. We also consider this possibility. It is. One might more or less cook up a general theory starting from braided vector spaces and some, but at the end of the day, it's not really worth the effort. Essentially, yeah, everything works also in that language.
Okay, thank you. And second question, you mentioned triangular decomposition and that you have different proof than usual. Could you say a little bit about it?
Yeah, let me see whether I can offer you quite quickly. I had here. Well, let's put it this way. I'll give you here, I'll introduce when I write the why can't I succeed in having this? Okay, here we are. Can you see the condivision now? Yeah. Do I have it?
Not yet.
Yeah.
I see the tablet has started screen sharing, but not yet.
Yeah, but it's not sharing.
Well, it's starting to share.
But not completing it.
Yeah. That's weird.
Okay, anyway, let's say what's the content of the triangular decomposition theory. You are claiming that your Hopf algebra as a model is isomorphic with the tensor product of, say, negative part, Cartan part, and positive part. So now the idea is as follows. You identify the negative Cartan and positive part as being subalgebras inside your entire quantum algebra. Okay? Good. Now, okay, it works. So your PBV, no, it's not PBV. Your triangular decomposition result goes as follows, and again, it doesn't work. Okay, it works. Can you read it now? So, triangular decomposition theorem. Something of this kind, you have, say, U minus, tensor, U0, tensor, U plus. You want an isomorphism here, which should not be anything. You really want it to be the product. That is, you start with something of this type. You use the multiplication inside your algebra to take this product, and then you get it inside here. You want this to be an isomorphism, a linear isomorphism, say. Okay? So the idea goes as follows. We, how does it work? We introduced here an algebra structure. So how do we do it? We essentially do the following. You take each one of these as being a subalgebra. So the algebra structure is such that if you are taking plus minus inside here, that's this is an embedding. So the left part is a subalgebra inside it. The same for the right part, and the same for the central part. So you want an algebra structure here for which the three factors are subalgebras. Good. So what do you really need? You only need to define the products for factors coming from different parts of this tensor product. So you have to define what is the product, say, of something of this kind and something of this kind, which is easy. You just take this tensor product, for instance. Okay. The key point is, okay, but I want to define also a product in the other order. And the idea is, okay, this will be something of this form, which I already have, plus a bracket. Okay. Now, the idea is I already have this object, this product, and what do I take as commutator? I take the same commutator that I would find inside here. In other words, I'm looking for an algebraic structure here such that this same map will be not only an isomorphism of algebras, of modules, but also an isomorphism of algebras. But this requirement somehow tells you what your algebraic structure must be, because it tells you how to define all these products. The point is, you give the definition for these objects through their generators. So here I have generators of Cartan type. Here I have generators of type F5. So you define your products following this rule, but you are giving a definition on generators. So you have to check that the definition respects the relations that you already have here. So there are some computations to be done, but you succeed. And so at the end of the day, you have an algebra structure here, which is exactly the same that you have there. The generators here obey the same relations that you have on the right. So at the end of the day, you can produce at least a morphism in this direction, because each generator here corresponds to a generator there. The relations which are respected here are already respected there, and so you have at least an epimorphism. But then it is also an isomorphism because you can invert the map, essentially. Now I'm certainly forgetting some details, but the idea is to introduce here by hands an algebraic structure which forces your map to be even more than a linear isomorphism. It will be an algebra isomorphism.
Okay, and because you have this algebra structure on the left, you have arrow by the universal property for algebra on the right. Yeah,
that's the point. But you cannot apply a universal property if you have not an algebra structure on the left hand side. So you first have to introduce the algebra structure in the clever way, in a way that the relations obeyed already in the whole algebra are still respected. You can apply the same idea to obtain a triangular decomposition for the universal enveloping algebra of your semi-simple algebra, for instance. It's the same idea. The computations will be slightly simpler because instead of having quantum state relations to take into account, you have simpler relations, but it's the same philosophy. It's an argument which has nothing to do with quantum stuff, if you want.
Mm-hmm. Thank you very much.
That's why we were surprised and somewhat pleased of this result.
Okie dokie. Any other questions? I don't see any raised hands. So in this case, let us grazie mille our speaker again. Thank you so much, Fabio. Thank you.
Thank you.
You're welcome. Thank you very much to all of you for your attention.
So let me stop.
Ciao, Rita.
Oh, hello, Rita.
So at the end, she became visible.